In this small lecture, we'll study how to get the volume of M ball. The unit interval -1 to 1 can be rewritten as in this equation. So x squared is bounded by 1. Similarly, the unit circle and the unit sphere of radius 1 can be expressed in this equation. B2 is the unit circle, which is the point in xy such that x squared plus y squared is bounded by 1. And B3 is the unit sphere, which is the collection of points x, y, z such that square sum is bounded by 1. In general, n-dimensional ball or M ball of radius r is defined as in this equation. B and r, n indicates the dimension, r indicates the radius. There is collection of points, and the square sum is bounded by r squared. It is possible to define volume of M ball of radius r, and there is a V and R. There is a volume of the M ball. In one dimension, it is length, and in two-dimensional area, it is area, and in R3, it is the ordinary volume. And when n is larger than or equal to 4, it is called a hypervolume. Here, for example, a volume of one ball of radius r, that is 1, so that is now, in fact, for this one, x squared is bounded by r squared. So the interval is minus r to r, so the length is 2r. Similarly, the ball of radius r in 2D, that is disk of radius r, we know the area is pi r squared. In 3D, the sphere of radius r, it has the volume 4/3 pi r cubed. For every of these volume, we can get in this way. The volume of M ball of radius r can be obtained from this formula. First, we try to get M ball of radius 1 and r to the n is multiplied. In this one, now here, the volume, so the length of unit interval is 2, and for general r is multiplied. Now for the circle of radius 1, we have area pi. Now for general r radius is pi r squared. So that is r is multiplied here. There's r squared is multiplied, and there's r cubed is multiplied. So this portion is a volume of unit sphere. Right? So once we can get the volume, hypervolume of unit ball, unit M ball, then we can get the volume of M ball of radius r by multiplying that one, r to the n. Okay, here we have a challenge. We define now Bn is the n-dimensional ball of radius 1. So it's a radius 1, so that we know this 1. And its corresponding volume is now Vn. We'll try to use polar coordinates to find Vn, the volume of the unit M ball. For n is larger than or equal to 4. In order to get the volume of n ball of radius 1, we start with this figure. Now, in this x1 direction, x2 direction, and everything over there is from x3 to xn. Then, now, in this plane, we try to use polar coordinates so that each point is r theta. But anyway, for each point, which is now x1, x2, and at the point, the whole volume is now, looks like the height is n minus 2 ball of radius 1 minus square root of 1 minus r squared. Let's see when, for example, here n is 3. Then, okay, for example, n is 3, then we know that this one is now x1 squared plus x2 squared plus x3 squared, in fact x, y, z, and that is bounded by 1. So here in x1, x2 direction, and it's now r, so that's r squared. So that means that x3 squared, the height direction, is 1 minus that x1 squared plus x2 squared, which is in this notation, it will be 1 minus r squared. Right? So that here, once we solve it, then x3 is minus square root of 1 minus r squared and plus square root of 1 minus r squared. So that is, bottom is minus this quantity, and top is that one. Of course, this height from the beginning to the end is exactly, that is now twice of this quantity. That is now 1 ball of radius 1 minus r squared. So that from here, the length is twice of square root of 1 minus r squared. We already know that volume of 1 ball is 2 times r, where that's r is playing the role of r radius. So we can say that when n is 3, from here to there is 1 ball of radius square root of 1 minus r squared. In general, okay, we have n dimension. We put here x1 direction, x2 direction. Remaining directions, coordinates are in this direction. Then, for each point, we may consider the height from here to there is the volume of n minus 2 ball of radius square root of 1 minus r squared. Now, that is the domain when we try to get integration. So that is now from 0 to 2 pi in polar coordinates. Radius is moving from 0 to 1. And there's a volume of n minus 2 ball. So there is a v n minus 2. And radius square root of 1 minus r squared. So this quantity n minus 2 power. And here in polar coordinates, the integration must be here r dr d theta, right? Okay. This portion is theta independent, and that is constant. Okay, first we put this one constant outside, and there's a theta independent, so that we can get from this integration in d theta, we can get 2 pi, and remaining part is now r integration. You can get this one quite easily, and if you finish the calculation, then you can get this one is now 1 over, and you can easily get it. So we recheck this formula. Vn, n-dimensional volume of unit n ball, is the same as 2 pi over n and Vn minus 1. So we found a recursive formula for volume of the unit n balls. Okay, let's see some examples. We know that V1 is 2, the unit interval minus 1 to 1, the length is 2, and V2 is pi, the disk of radius 1 on the plane, pi r squared r is 1, so we have pi. From here, we may use the formula. V3 is 2 pi over 3 V1, V1 is 2, so that we recheck that quantity. That is exactly the same as here. Now, when r is 1, we have that one. So we have a consistent result. V4 is from V2, we can get, by scaling this one, we have that one. And you can continue here. V5 is now 2 pi over 5 V3. So you can get. So that later on, once n is larger than 6, then 2 pi over n is less than 1, so that the numeric value of Vn is decreasing. In the beginning, right now is increasing. Now, okay, here V4 is larger than V2, and V5 is must be larger than V3. Now V6 must be larger than V4, but after that, there is no guarantee. But because of this jumping relation, in fact, V5 is the largest quantity, and then it's shrinking, and as n increases, the numeric value is approaching 0. But that is the volume of unit n ball. Once you consider general radius r, then r to the n must be multiplied. Okay? Okay, that's how to get the volume of n ball. Thank you.